Hi students, today we are discussing about the second part of rotational dynamics, that is the rotational motion. In that rotational motion, first most important point is the moment of inertia, and therefore first point is given moment of inertia as an analogous quantity for the mass. We know that in 11th standard or last year we studied the angular displacement, angular velocity, and angular acceleration respectively replaces displacement, velocity, and acceleration for various kinematical equations. Also, torque is an analogous quantity for mass. The expressions of linear momentum, force, and kinetic energy includes mass as a common term. Already we know that in that force F is equal to ma, or kinetic energy K is equal to half ma square. That means their mass as a common term. If we open the door with hangers, we give a angular displacement to it. The efforts needed for this depends not only upon the mass of door but also the perpendicular distance from the axis of rotation where we apply the force, and thus the quantity analogous to mass includes not only mass but also distribution of mass around the axis of rotation. To know exact relation, let us derive an expression for the rotational kinetic energy of a rigid body. Therefore, consider this is a rigid body and this is the axis of rotation. Axis of rotation. Suppose this is axis of rotation. This rigid body is continuously rotating with constant angular velocity, that is omega. This rigid body is made up of large number of particles, that is n number of particles, and that's why we are taking some particles of that. First particle of that body of mass m1, which is situated at a perpendicular distance r1 from the axis of rotation. This is axis of rotation which this rigid body continuously rotates with angular velocity omega. So that rigid body made up of large number of particles. Out of that, first particle of mass m1 which is situated at a perpendicular distance r1 from the axis of rotation. Second particle we are taking here, m2 is the second particle, and which is also situated at a distance r2 from the axis of rotation. And last particle we are taking the nth particle, that is we can say that mass of that particle is mn, and distance of that particle also rn is the perpendicular distance from the axis of rotation. Now the rigid body which having the constant angular velocity, but the linear velocities of these particles are different, and that's why the linear velocity of first particle of mass m1 can be given as phi1 is equal to r1 omega. Phi1 is equal to, this is the linear velocity of first particle of mass m1, therefore phi1 is equal to r1 omega. Same way, second particle, the linear velocity of second particle is given by phi2 is equal to r2 omega, and so on. And last particle we are taking there, mn is the mass of the nth particle, and that's why phi n, linear velocity of that particle, phi n is equal to rn omega. These are the linear velocities of that respective particles. We have to calculate here the rotational kinetic energy of that rigid body. So this is for, these are the velocity, linear velocity of that respective particles. Therefore, the kinetic energy of that particle, respective particle. So kinetic energy of that first particle of mass m1 is given by the formula Ke1. We can write here Ke1 is equal to half m1 phi1 square. that is kinetic energy is equal to half mv square we can write. So this is the kinetic energy of that first particle of mass m1, and that's why we can write k1 is equal to ke1, kinetic energy 1, ke1 is equal to half m1 phi1 square. But already we know the phi1 is equal to what, r1 omega, and that's why we can write that ke is equal to ke1 kinetic energy, ke1 is equal to half m1 phi1 square means what, that is r1 square omega square, that is v1 is equal to r1. That's why we can write v1 r1 m1 r1 square omega square. Same way, this is the kinetic energy of that first particle of mass m1. Kinetic energy of second particle is given by the formula ke2. We can write there ke2 is equal to half m2 r2 square omega square. Similar way we can take in here also v2 is equal to r2 omega, and that's why you can write direct this equation as ke2 is equal to, that is kinetic energy of second particle of mass m2 is given by half m2 r2 square omega square. And similar way the kinetic ken we can write here, kinetic energy of that nth particle of mass mn is equal to half mn rn square omega square. So we have to find the kinetic energy of that rotating body, and we calculate here the kinetic energy of that respective particles. And therefore when we add that kinetic energy, all particles, summation of all these kinetic energy of that respective particle, then we get the kinetic energy of that rotating body. So we can write here Ke rotational is equal to summation of all this kinetic energy, that is the ke1 plus ke2 plus ke3 plus dash 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 so on last ke(n). Put that magnitudes, already we calculate that. First ke1 half m1 r1 square omega square plus ke2 half m2 r2 square omega square plus last dash 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 last one half mn rn square omega square. When we take a common, that is half omega square, and remaining quantity that we write in bracket m1 r1 square plus m2 r2 square plus dash 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 plus mn rn square, and this can be written as ke rotational is equal to half omega square. This may be written as summation which having limit I is equal to 1 to n, that is mi ri square. And that's why we can this quantity is nothing but this quantity is called as moment of inertia, and that's why we can write ke rotational is equal to half, that is omega square into moment of inertia, that is I. So we can write this equation as ke rotational half I omega square. Say this equation number 1. Okay, so here I is the moment of inertia, therefore moment of inertia I is equal to, we got that formula, summation which having limit I is equal to 1 to n mi ri square, where that I is called as moment of inertia. So this equation number 1, ke rotational. In case of translational kinetic energy, we can write that similar formula as ke translational is equal to half m phi square. See this equation number 2. Now ke rotational, already we calculate ke rotational and ke translational by using the two equations, half here m, here I, here phi square, that is the linear velocities are square, and here omega square means this angular velocity. These are the velocities, that means this m and this r. That means in the rotational motion I plays that role, same role is played by mass in a translational motion, and that's why we can say that mass is, or moment of inertia is analogous quantity for mass, and that is our title, moment of inertia as an analogous quantity for the mass. So we can write m is analogous to I, or I is analogous to m. Now if we assume the object to be consisting of a finite number of particles, for homogeneous rigid object of mathematically integrable mass distribution, the moment of inertia is to be obtained by integration as I is equal to integration of r square dm, where dm is the small mass, or already we know I is equal to integration of r square dm. So I is equal to, already we calculate I is equal to summation which having limit I is equal to 1 to n mi ri square. But the object which is consist of a finite number of particles, or for the homogeneous rigid object, mathematically we can write that moment of inertia is to be obtained by integration I is equal to integration of r square dm. If the integrated or integrable mass is not known, then in that case it is not possible to obtain the moment of inertia theoretically, but it can be determined by experimentally. We can determine that therefore another formula for moment of inertia I is equal to integration of r square dm. Then the next point in that rotational motion is the moment of inertia of a ring. Moment of inertia of a ring. Moment of inertia of a ring.